Wonderful. Well, thank you very much, everybody, for coming back. Right now, we've got a wonderful session on automating tune-up and various procedures like this using machine learning. First up, we've got Hendrik Bluhm, who will be talking about using machine learning to automate quantum dot operations. Hendrik?
Okay.
Oh, one other thing I forgot to mention. We've got a relatively small number of attendees here. So if any of you have questions at any time, feel free to raise your hand and we'll deal with it.
Sounds good. Yeah, I can also take questions during the talk, especially if it's directly related to some of the things or if something is clear. So yeah, thanks a lot for having us here and for keeping us together even in times without travel. So indeed, I'll be talking about the tune-up, various tune-up problems from the perspective of quantum dot qubits. And in some sense, it will be even a little bit broader than just machine learning, or take machine learning from a somewhat holistic point of view. So here we go. So let me just elaborate a little bit on the devices that this is applies to, and it's basically all kinds of electrostatic quantum dots. The pioneering or legacy devices here would be in gallium arsenide heterostructures. Nowadays, silicon, germanium, or various silicon MOS types are more prominent. And what they all have in common is that one tries to capture individual electrons through a combination of band structure engineering, which then is typically fixed and doesn't need to be tuned. But for lateral confinement, one uses electrostatic gating to define the potentials that capture individual electrons. And that is one of the aspects that needs to be tuned carefully. And one might even say that compared to most other qubits, this aspect is more demanding because there are more parameters that need to be adjusted than, for example, for superconducting qubits. And if you then look at what it takes to tune these, the first aspect is what we like to call coarse tuning, is to even form a quantum dot. If you start with a virgin device without any voltages on the gates, all you have is a bunch of electrons, way too many. Then one needs to apply the right amount of voltage to capture these individual electrons, have the right tunnel barrier so that these quantum dots where few electrons or single electrons can sit. Once this is done, which is in some way even the hardest part or hardest to automate, one typically still wants to fine-tune that to make the qubit operation possible, which means that the tunnel coupling, say between different dots, also from a dot to the lead, is adjusted to the desired value to run the operations, couple the qubits, and also do initialization. Or furthermore, one wants to find the operating points at what voltages, for example, an electron can be exchanged with the leads for initialization and readout. Then once this is done, you have your qubit. You want to calibrate actual gate operations, the high frequency pulses that are either directly applied to some of these gates or to microwave antennas, microwave wires, and then drive the qubit. And finally, what I'll touch on also in the end is how to read out the signal in an optimal way using either neural networks or a Bayesian approach and actually comparing the two. So I'll give a brief outline of what I'll cover here, and I'll sample each of these aspects, but of course, I think no one of us has the golden bullet for all of them. I'll start on the quantum dot formation, where the challenge is to adjust the gate voltages again on these gates to have the desired potential. What is plotted here is the electron density that would result from a simulation. And you see that there's quite a few number of gates that adjust that in a somewhat indirect and strongly interdependent way. Depends also on the device design, which makes that a non-trivial task. And what I'll focus on here is how to interpret data with convolutional neural networks, basically building and elaborating on the talk by Justina Swolok that we saw on Tuesday, where we've actually built on. What then is required is to, first of all, have the right quantum dot occupancy in each of the dots, and also have the tunnel coupling in the right ballpark that electrons can move in and out and travel between two dots without them completely joining. Then the next step is the fine-tuning of the tunnel coupling. And what we have done here is to develop an approach that is basically kind of a Bayesian or statistics-based machine learning approach, which fine-tunes these two tunnel barriers And the starting point for that is, first of all, a systematic way based on conventional fits to extract the parameters here, and then followed by an iterative gradient-based tuning algorithm that allows us to tune two tunnel couplings simultaneously and make significant changes just in a few iterations, as I'll show up here. And then I'll move on to tuning actual gate operations and show you that on these devices we can tune pulse sets, single qubit pulse sets with up to 53 parameters on the experiment in a closed loop calibration way, and also discuss a bit more generally how this calibration procedure could be generalized to multi-qubit gates, in particular with respect to tune-up sequences that can be used to extract the errors with a focus on only the systematic errors that one can correct, while decoherence is kind of taken as given and is taken less effort to measure from the system. And then the final part will be some work on readout discrimination, where we looked at the task that needs to be carried out when determining the spin state was one of the methods that's typically used. I'll explain that, and compared the neural network approach versus an optimal Bayesian approach, and find that both actually have a very similar performance in terms of fidelity and also computational overhead, which of course is somewhat hardware dependent. But it turns out that an advantage of the neural network is that it's more robust due to some kind of built-in calibration feature that otherwise for the Bayesian approach would have to be added on top in some way by hand or with additional characterization. So perhaps a few general considerations before I start. I think when thinking of machine learning, it's useful to also include conventional statistical or iterative algorithms. In the end, the decisive part is not so much to use machine learning, but to get our tuning jobs done, as is reflected in our question number 2. So I also take a somewhat holistic point of view here. And furthermore, it's very useful to do benchmarking of different approaches. So I think it's valuable to not only say, oh, look, we can do something, it's cool, we can do something with a neural network, but really compare how do the different approaches compete or compare to each other to guide us as a community what is the best approach and when one works better compared to the other. And I'll certainly don't have a golden bullet there, but try to touch on that in the various points to at least give some reference data. And then finally, what I think is in common for these is a set of requirements. And what this tuning all has in common, or these tuning methods have in common, is that they use input from experiments, which is typically more costly than just evaluating a numerical function. That means one wants to do relatively few measurements. And second, perhaps even more important, since measurements have inherently more noise than typical numerical simulations, the tuning algorithm somehow must be noise tolerant and be able to deal with the uncertainty without becoming unstable or losing convergence properties. Okay, so here's the outline. I've just basically given a brief overview of the qubit systems. I'll elaborate on that where needed and what are the tuning needs. And then we'll basically now cover these 5 different aspects that need to be tuned on the way from building a quantum dot or forming a quantum dot to running it and operating it as a qubit. So let me start with the forming the quantum dots. And the general idea here is that one has some kind of algorithm that is used to tune that, which acquires data from the dot. And the typical feature that you've already seen in the previous talk by Justina on Tuesday is that one measures these charge diagram. What is looked at there is the response of the system to changes in the gate voltages. This is then interpreted in a certain way. Currently, this is done by a human who decides then, well, how do I change the gate voltage to make my diagram look the way I want it and tune the device in the correct way. So we change the voltages that are applied to all the gates. And well, once we're happy, this is done. And the idea here is, of course, to replace the human, make that automated. And what I focus on is how to do the classification here using a machine learning approach. A few words on these charge diagrams to make sure you know what that means and where they come from. When forming these devices, it is common to select 2 of the gates that control the occupancy, for example, of a double dot. It's nice to have 2 dots or single out 2 dots if you have a multiple quantum dot device, because you can get 2-dimensional data, sweep the voltages, and measure the response of a charge sensor next to the device. And what you then get is a diagram, a color plot here, where the color axis shows the charge sensor response as a function of, sorry about that, the 2 gate voltages, VL and VR. And the important features are these transition lines here. That may be a little bit of background, but that can be subtracted. So the important features are the transition lines. And whenever you see a step, you know that an electron is added or removed from the dot. And from the shape of these transition lines, one can extract the tunnel couplings and also charge coupling. And by counting from the position where there's no electrons left, determine how many electrons do I have present here at all. Here's a typical zoomed version where one just focuses on one transition between, say, the 1, 1, where each number reflects the number of electrons in the dot and the 0, 2 state. That's a common way or common place to operate these double quantum dots as qubits. And so the task will be to interpret these diagrams here and guide this tuning process. Now here's a variety of different scans that are, well, not as pretty as the previous ones and not as nice as you typically see in publications, but, and one could certainly optimize them further, but they are in some way real life on a setup that is perhaps not quite optimized for signal to noise, or where you measure fast and want to have a high throughput. So that means one sees more noise rather than spending lots of time on averaging. And also the device quality can vary, so one doesn't always get the pristine, nice pictures. But what you see here basically are these transition lines. Here's differentiated, so each transition just shows up as a maximum. And from the slope, if they're more horizontal or vertical, if there's a single set of lines, you know that you either have one single quantum dot more on the left or more on the right. If you have diagonal slopes, it would be more quantum dot in the middle. And if you have double dots, you see these so-called honeycomb features with the kind of lines that merge and then diverge again. And depending on how strong the tunnel coupling is, so if you have a large barrier or a small barrier, these lines are either, well, have clear kinks or just a little bit wavy. So this is the kind of distinction that needs to be done using a classifier. And well, in some way, what well, the merit or message here is of our work compared to earlier one is how robust are machine learning approaches to a suboptimal signal to noise, which then gives you more freedom to measure quickly and well, make the whole thing more robust, and also deal with moderate device and data quality, which is perhaps ideally not so important in a highly scalable quantum computer, but will be crucial if one wants to characterize devices in large numbers to give feedback to fabrication processes, which is one of the current trends in the field of semiconductor qubits, where foundries are entering the field, are churning on millions or large numbers of devices, and then want to have feedback and know, well, how well do these work, how reliable are they, and that's not doable with the current methods. So our starting point was actually the, well, earlier work by the group of Justina Zolak, using a small convolutional network to interpret these charge diagrams. And well, we wanted to ask, well, how does that work for our data? Can we adopt that? And when doing that, we found several issues. Here are just 2 examples. One is that we see strong overfitting. So what you see here is the accuracy of the classification of the training data as a function of the iteration numbers. And one sees that while training or iterating the training of the network, the training results get better and better. Testing it on a different data set on which has not been trained stalls, doesn't get better, which is a sign of overfitting and means that the procedure isn't quite ideal yet. Another effect that we found is that when switching the device to a different cooldown, which had a somewhat different noise characteristic or different behavior, the results change a lot. So you see here 2 histograms of the classification certainty distribution, so a measure of how sure the neural network is that it has correctly classified it. And on the training data, you see that these, for various outcomes, typically center far to the right, meaning that in most cases has a very high confidence in the result. This changes completely when trying with a new set. And that means that it can be that the neural network needs to be retrained when working with a different device or a different experimental setup. And well, we then try to optimize that a little bit. One aspect was this retraining. We used an automated optimization of the network geometry and hyperparameters using appropriate optimizer, and then also introduced a rejection of input with low certainty, which I think is allowed because if you find a data set that cannot be classified, it's always possible to repeat the measurement at moderate cost. And with that, we found that one can retain a high accuracy in the identification for our data sets at 94%, and even reduce the number of parameters compared to the human design network that we started out with. So efficiency is gained a little bit by this hyper optimization. And the overall conclusion that we draw from that is that the transfer of one, say, published approach to average data quality is possible, but not trivial. It requires work. Concretely, these were kind of 1.5 bachelor theses for us. It requires a significant retraining effort, and retraining often means if you don't have a good reference and cannot use simulations because they're not realistic enough, which more or less was what we found, means manual labeling of the results, which is a significant human effort. And so I think overall, we haven't quite found the golden bullet yet, and there's significant room for improved standard procedures that could be used as a resource by the community to achieve this task. So more things to do. Now I'd like to briefly touch then on completely automating the coarse tuning. So all I've shown you so far is to interpret this charge diagram, but the decision of what to do, how to adjust the voltage, still needs to be outside. And here's one example from the group of Bluhm and van der Sijpen from a couple of years ago, where this was achieved on a quadruple quantum dot device. For the interpretation, they actually use conventional image processing procedures, for example, convolving the charge scan here with the ideal outcome. And then if you see something that matches the intended outcome, you see a maximum in the convolution. And with that, they could show that it is impossible to automatically tune this device into the single electron regime, typically overnight. But it hasn't really been adopted much since then. The group has moved on, and we are currently working on turning this proof of concept aspect into a tool that can really facilitate the characterization and study of large number of devices with good human efficiency. So looking forward to, it will be interesting to see what comes out and how useful this will be. Okay, so much about the quantum dot tuning, and so the formation of quantum dots, coarse tuning, capturing electrons. I'd like to move on now with a machine learning approach for fine-tuning the gate voltages, so basically taking the next step. And this also, just as a for reference, there's been some similar work also from the group of Bluhm and van der Sijpen here on a triple dot, where the idea is to, well, you want to target a certain tunnel coupling between the devices. One uses a measurement procedure that can determine this tunnel coupling. I'll explain how this works. Then calculate typically virtual gates. These are linear combination of gate voltage changes here that are designed to just change the desired tunnel coupling, but not in particular the occupancy of the dots. Then it's remeasured, and if the result is good, the algorithm exits. If not, one predicts a change to this tunnel coupling. And down here you see the performance, where, for example, changing the tunnel coupling from a few micro EV to a few tens of micro EV, roughly in order of magnitude, is possible in certainly less than 10 iterations. And what I should emphasize here is that here a single tunnel coupling between one pair of dots was tuned at the time, which means it's a linear or single parameter tuning task, which is not the maximum of complexity one can reach. Now, before elaborating on that, I think, well, here we took the approach that rather than using the kind of imaging or charge diagram interpretation, which is always somewhat qualitative, we used a number of physically motivated measurements that can extract the parameters from the devices and define the set of characterization procedures that can then give the input target parameters or the values that are compared to the targets for tuning up the number of devices. And I'll briefly walk you through that. It starts out from looking at how the transitions of the electrons, so these steps in the charge diagrams, change when adjusting the gate voltage, and that gives us cross capacitances and lever arms. Then the next step is to look at the tunneling rates. Here the procedure is to change the voltage and see in real time with repetitive signal averaging how fast an electron can tunnel in and out of the dot. And then this exponential decay that can be fitted tells us what are the typical tunneling rates going into the dot or out of the dot. And this can be done for several leads. So here you see two different values with a few hundred nanoseconds or tens of nanosecond time. If this is, if the tunneling is too fast to be resolved, if the resolution of the setup is not high enough, one can use a different approach, which is basically looking at how long it takes to initialize the electron, how fast it can, or how fast the spins can relax to the ground state. And here you see then again an exponential decay of the initial excited state to the ground state as a function of wait time. This is then only limited by the control instrument and not the readout bandwidths, where one can go into the sub 10 nanosecond regime quite easily. The next step is to look at the tunnel coupling between quantum dots. So what I've discussed so far was the rate of tunneling in and out of the dot. For measuring the tunnel coupling between dots, one typically sweeps a gate voltage combination that transfers an electron from one dot to the other. And then the width of this transition, basically a broadening due to the tunneling, gives a measure of how strong the coupling is between these two dots. So that gives us an additional parameter. And then last but not least, one can look at certain other operating points. In this case, these two plots here represent the operating points or voltages at which certain operations, in this case to quiet down nuclear spins in a gallium arsenide device, are taken. So perhaps as reference, each of these measurements takes, say, less than a minute, perhaps a couple of seconds even, can then be fitted with a standard routine, and with good data quality, this can be quite reliable. Now, once you have that, you know what are your current parameters. Does your device do what you want? And then you can tune that. And what we did here as a test problem is to simultaneously tune the tunnel coupling between these two quantum dots, as well as the tunnel coupling to the lead. So a two-parameter tuning task, and that's in some sense a minimum that needs to be controlled to operate this as a qubit. This is done, the tuning is done by adjusting the voltages on these red gates that affect these tunnel barriers. The procedure then is again iterative. We measure the parameters and adjust the voltages. And what you chose to do here is to do a Newton update, meaning that the new gate voltages are obtained from the deviation between the measured and the desired value multiplied with the inverse Jacobian of the system. And then, of course, you ask yourself, well, where does this Jacobian come from, which reflects the linearized system response. And well, why did we do that? If you had a linear system, then this would be an exact single step adjustment. If you have a nonlinearity, one can still have superlinear convergence if this Jacobian is known sufficiently well. So it should be a nice algorithm that can deal with very few iterations. But as I said, we need to know how to get this Jacobian. And the idea here is, well, one could use finite differences, but these are typically costly, require a lot of measurements. And therefore, we took an approach that in some way is a machine learning approach and mimics a little bit how a human operator proceeds. Namely, one tries an update based on the expected behavior. That would be the current best guess of the Jacobian, and then sees what comes out and revises these expectations, meaning the statistics or the probability distribution representing the Jacobian based on the result, and then uses the intrinsic updates or the steps one does anyway to update the Jacobian as one moves along. And so Concretely, we've modeled the Jacobian as a multivariable Gaussian distribution. So we take uncertainty into account, which reflects noisy measurements and imperfect information, also drift. And then at each step, update this distribution according to information gained using a Bayes approach. And that also allows us to consider noise in the measurements in a natural way. Here are the equations for that. I will not go through in detail, but basically there's update rules for both the mean and the covariance of this distribution. And what enters there are, first of all, the measurement results, also a matrix that encodes what was actually measured. Similar for the covariance, an important factor is this Kalman gain that basically tells you how much the new information updates the distribution. A comment here is if one simplifies that to zero measurement noise, takes the limit, then this reduces to Broyden's method, which is a known iterative tuning scheme. And one can think of this whole approach as making the minimal change of the Jacobian to make it consistent with each measurement. And this algorithm then is without noise, also known to have superlinear convergence. So it should have nice mathematical properties. Now here's then the approach or the proof on the experiment where we've iterated this loop, measuring, update in each step the gradient, and then adjust the voltages based on the current knowledge of the system response, and then repeatedly run through this loop until we reach the target parameter. And here you see a run of basically continuously iterating this algorithm. It's somewhat noisy, there's outliers, but whenever the target value represented by the blue lines here is changed, it typically takes about 3 iterations to go from one value to the other and changing the tunnel couplings by a factor of 2 or 3, depending on which one you look. And what's particularly nice is that one can simultaneously tune these parameters. So the 2 data sets were taken in parallel, and you see that adjusting the target of one has relatively little effect on the other, which basically stays at the value or at least recovers quickly. A few comments here, and to maybe trigger some thinking about algorithms and procedures more than the device physics, which I think is more of interest here in this community. What I think is nice here is that one has a fast gradient-based method that uses the advantage of gradients without real extra cost to determine the Jacobian, which of course only works as long as it doesn't change too much from one iteration to the other. Given that the update rule can take noise into account and then leads only to partial updates, there's an intrinsic robustness against outliers, and the occasional erroneous measurement should not throw off the procedure immediately. One can also extend this to model, say, drift, so slow fluctuations in the system, or voltage dependence of the Jacobian. So if it changes as a function of the operating point where one operates the device, via an extra kind of effective noise term that takes this uncertainty into account. On the other hand, we found that if one has large errors in the Jacobian, then not so surprisingly, this causes oscillatory behavior. So one needs to watch a little bit for the convergence behavior. And one thing that I would find quite interesting to see is a systematic convergence analysis and benchmarking against other algorithms. Being experimentalists, we've only focused on a practical demonstration of this algorithm. Okay, so much about fine-tuning tunnel barriers. What I'd now like to move to is using feedback tuning for high fidelity qubit control and how this also could be extended to tuning up 2 qubit gates. And well, the approach we took here is what Shai Machnas on Tuesday related to as making a mistake. So our argument was that any model that we have of an experiment will have inaccuracies, and it's very hard to calibrate this model and even make it capable and flexible enough to fully reflect the device behavior. So we just accept with certain and live with systematic errors, and then said, well, if they're small enough, we can fine-tune the pulses on the experiment without really worrying about the model accuracy. Let me just see. Yeah, so there was a question relating back to the previous slide. Maybe I'll just pick that up. If I'm in the case where I'm changing the parameter to learn, how do I ensure that the system does not learn the periodicity of the changes? So that's a good question. I would think that given that, this is an approach that doesn't really have a long time memory. It's basically local update set that only takes this Jacobian as a system response and the current situation into account. I doubt that the system would really remember basically that what I'm doing here at one position really is an undoing of what I did 20 iterations earlier. What might happen, and we've partially seen that, is that the parameters to which it converges does depend a little bit on the periodicity. And so, for example, since the recalibration of or the probing of the Jacobian also depends on making these steps, it might be that the gains that need to be adjusted manually, I haven't talked about these, might in the end depend a bit on the tuning. So there are some things that would have to be studied further to see how stable and robust this approach is. All right, so let me continue here on the modeling. So the approach we took here is to start with an open loop model where we took a qualitatively correct, especially a model which especially has realistic noise values, predict or compute an optimal pulse based with optimal control theory, then feed this into an experimental optimization loop, execute some gate sequences, perform measurements that tell us how these gates perform. And based on these, what we call error syndromes, so these average measurement results, update the gates until we are happy with the outcome, and then do randomized benchmarking as an independent verification. A few words here on the system, how the particular qubit is controlled. We use here as one of our specialties that is particularly advantageous in gallium arsenide, 2 electron spins as 1 qubit using the M=0 subspace, so only the anti-parallel configurations of the 2 spin states to encode a qubit. And that has the big advantage that one can use fully electrical control only through voltages on the gates using the exchange interaction between these 2 spins, which makes it very fast and avoids the need for microwaves. So you can get by with low power and also reduce crosstalk because the frequencies are lower. And since this manipulation is fast, it helps to beat dephasing due to nuclear spins in the system. Here's then a typical pulse that comes out of this numerical optimization as a function of time. So it's typically a length of a few tens of nanoseconds. Here you see the voltage, a few millivolts applied to the system. And down here is the corresponding exchange interaction that couples the 2 spins and basically corresponds to Hamiltonian along one axis of the Bloch sphere. You can think of this as a very strong Rabi drive where basically a pi/2 pulse, which is shown here, is executed with just 3 oscillations of the drive field. And then, of course, there's all sorts of nonlinearities that come into play. But by tuning these pulses, one can affect any operation one wants. Here's a trajectory shown for a particular initial state under this pulse doing then this pi/2 operation. In terms of parameterizing that, we've basically taken the maximum that our hardware can provide, looking at the amplitude of the pulse at each sample. So basically allowing a change in every nanosecond, which then leads to about 25 parameters per pulse, just given by the length, and also take the finite rise time into account. That is basically a real life effect that any real hardware will have. And well, then coming more to the methodology, a challenge here is that one only has a limited reference available. If you just apply a pulse, it's not so obvious to tell if it does the right thing or not. And the approach we took here is to simultaneously tune 2 pulses self-consistently, which then gives enough of a reference similar to gate set tomography, but in a much reduced version for those who know that. And the idea is to measure different pulse combinations with one single preparation and readout axis. And that allows one then to extract syndromes that can separate all the linear independent error generators, such as over-rotation or axis errors of the individual qubit operations. Then based on these syndromes, the gates are adjusted and iterated to null all the syndromes until all systematic errors have, to the sufficient accuracy, been eliminated. So here's an example of the syndromes that are taken, and I will not go through all of them, but first of all, there are 6 of them, since for 2 pulses, one has 3 systematic errors, each of them with 3 parameters. And some of them are easy to understand. So for example, if one initializes in the 0 state here, then applies a pi/2 pulse, then the amount of over-rotation, so the average state after that, will reflect the over-rotation of this pulse. So by doing this, by measuring the qubit population after this pi/2 pulse, one gets a measure that is to lowest order linear in the over-rotation of this pulse. The same can be done for different pi/2 pulse around the y-axis, and the axis errors that are occurred and then retracted or obtained from various combination of pulses. And we included 2 sequences that are basically an inversion of the qubit in order to be sensitive to decoherence and not find solutions that converge to the center of the Bloch sphere. A few words on the algorithm. What we used is a Levenberg-Marquardt algorithm that nulls all these error syndromes and is then based on a gradient computed from finite differences. I'm not sure this is the smartest choice, but it was a simple one and it worked. I'll show you how well. And the general idea is that compared to the practice of just optimizing randomized benchmarking, the algorithm obtains more information about what is wrong with the gates, because it is basically given a vector value target function. But on the other hand, one has to ask, does this really give a speed up? Because also to extract more information, one needs more measurements. So this would be an interesting benchmarking task. What I can show you is, first of all, that it works. So we achieved a high gate fidelity of 99.5%. I think this is still the record for the system, which is significantly affected by nuclear spins and also in practice charge noise due to this exchange-driven drive. We also find a good agreement within a factor of 2 or so between our best effort model and the experimental results. So that's nice from the kind of device and qubit perspective. What's perhaps more interesting from the algorithm point of view is the convergence. So here you see a number of runs of this tuning procedure, and you see that indeed, as expected for a gradient-based approach, it converges largely within about 10 operations. These are quite lengthy due to the statistics, so take about 12 hours. And then after that, not much happens. What is interesting here is that the convergence seems to saturate in some way and saturate at a finite value. That's something we haven't quite figured out yet why that is the case. Well, thinking ahead, there's certainly room for improvements. For example, one problem is that if one wants to retain this quadratic Newton-like convergence, that means one needs to have very accurate gradients. And then the finite differences due to the noise become very costly. And I think it might be interesting to also switch to a Bayesian or Broyden's method as we used for the gate tuning here. And then spend less effort on the gradient update and maybe have a mix between quadratic and linear convergence. We also found that there's poor convergence if the target function locally approaches a minimum and without really having a zero crossing. So for example, for fidelity limitation due to noise. So I think it would be interesting to treat this as a constrained optimization. Also, what I wonder about is if one has more complex gates, if the radius of convergence can be a problem, that it becomes too sensitive, and if perhaps gates can be pre-optimized on the experiment to roughly get into the right region and then do this fine-tuning. Now, I'd like to briefly comment on 2-qubit gates. We've extended this approach of measurement sequences also to 2-qubit gates by basically numerically searching for gate sequences that extract all the 25 error syndromes that one has for a pair of single qubit and 1 2-qubit gate. And well, here are the different sequences shown, lengths 1 to 4, with different measurements on either one or the other qubit. And then also, well, applied that to one of these numerically optimized pulses. The details don't matter so much, but what you see here is the pulses applied to the exchange coupling between the well, 2 pairs of spins here. And so you see it's a well, moderately complex pulse shape, a little bit more complex than what we did on the single qubit gates also experimentally. And one can then look at the convergence behavior. First of all, this is a numerically simulated tuning. One sees that the final fidelity here as a function of the initial pulse error, as long as this initial error is not too large, remains more or less at the same value that one finds for an optimal starting point. The same applies for the leakage, so transitions from the computational subspace to different states. One can look at the success rate of the algorithm as a function of the initial infidelity. Not too large, it basically always succeeds. And here on the right, you see the convergence, basically the value of the syndrome as a function of iteration number, which also shows a pretty nice fast iteration, typically after, say, a handful on the order of 10 steps. All right. So now the last thing I'd like to briefly touch on is this single shot discrimination. And the task here is to find out if a spin is in an up or down state. There are various methods to read out spin qubits, but one that is particularly good for single spins is the so-called Elserman or energy selective readout, which uses or operates the device such that the excited spin state is above the Fermi energy of a lead. The ground spin state is below, and that means that the excited state can tunnel out and back a different ground state can tunnel in, whereas for the ground state, no tunneling is possible. And if one then monitors the occupancy of this quantum dot, again using a charge sensor as a function of time, if one is in an excited state, one sees this little blip here. If one is in a ground state, nothing is seen, and that can then be used to extract the qubit state that one had before the readout procedure. Here's a typical data set zoomed in. And what makes this analysis a little bit tricky, especially at low signal to noise, is that it's not known when these tunnel times happen. So this is a stochastic process, and you just know that over a typical time scale of the tunneling rate, this transition will happen if it's allowed, but it could be earlier or later, and the same back here. And that means that any simple averaging or linear filtering approach is not an option. There have been ideas like thresholding or wavelet analysis. They work quite nicely. But there's also an optimal Bayesian approach published by the group of Bill Keusch a couple of years ago. And what we did is to compare this approach with a neural network. I'll speed up here a little bit. It's a simple convolutional network trained with simulated data. And what we find is that if the network is trained well on simulated data, the performance of the Bayesian approach and the neural network are basically identical. What you see here is the readout error as a function of the signal to noise error ratio, which is the key input parameter. But one then sees in the details that the neural network is a little bit more robust towards parameter changes. So for example, if changing the neural signal to noise ratio, then the neural network can basically retain its performance, whereas the Bayesian approach does not perform very well or not optimally for parameters that do not correspond to the characterization or the input values. And so what you see from that is while the runtime performance in the ideal and also accuracy in the ideal case is similar, the neural network has a kind of self-calibration or a feature that allows it to be, without retraining, be used on different input data or with different noise strengths. So that could be a practical advantage. So with that, I'd like to conclude. Well, just mention that we've used that also for real readout. It increases the fidelity or visibility, so the performance is as good as other methods in the experiment. So with that, I'd like to conclude and just point out that we are trying to follow the philosophy to not only make the results, but also some code available to ease adoption. If you'd like to more tune to our website. And well, I have a few more slides on these, but I think I'll stop here in the interest of time. And would just like to thank our collaborators and the students working on that. This was a diverse effort with many people involved, running over years. And well, if you'd like to join the team, and our specialty is group sailing trips, we like each other so much that we stayed on a boat for a conference, then get in touch. We do have openings. Thanks for your attention, and I'd be happy to, well, if permitted, take a bit more questions.
Wonderful. Thank you very much, Hendrik. Great talk. So if I'd like to, if anybody's got a quick question, please put up your hand.
Okay, there was one by Timo Joas.
Yeah, go ahead, Timo.
Yeah, I'm maybe just unmuting myself. Thanks for the talk, Hendrik, and nice to meet you again. You said that for your machine learning approaches, you basically always run into overfitting. So is this related to just limited amount of training data, or do you see that you can add more and more labeled training data and it doesn't improve anymore for some reason?
Right, so this was the original finding that we found when just copying basically the network that was published before in the papers from Justina Swolak's group. And it probably does relate to having too little data. But given that one needs to manually label these diagrams to generate training data, that's generating more data is not such a pleasant thing to do. And that's in some sense is a disadvantage or an important parameter to optimize. And what of course one can do is stop the training early. I haven't mentioned that, and then prevent the overfitting.
So great, Hendrik. Actually, I've got a question, if you don't mind. So when you take a look at Bayesian approaches versus neural networks, from my perspective, there's a little bit of a tension that ends up showing up because the Bayesian methods tend to be highly interpretable. Yep. But often are much more difficult to hit the various specifics of the actual data that you end up seeing. So when it comes to tune-up, how do you end up seeing people reconciling the desire to have a powerful model versus having an interpretable model?
I mean, I see the problem and I can't really give an answer. I think we haven't really done enough yet, and enough systematic studies to look at these various effects, and would be very nice to have more in this direction. And one thing I can say is, for example, when looking at charge diagrams and looking at the intermediate layer of the neural networks, you can sort of partially understand what they mean. You see that they reflect certain features, but not in a completely predictable way. So, I basically say it would be very nice if the tuning and machine learning experts could give us a little bit more insight on that.
Cool. So, all right, we've got, we don't have time for this question, but I'm going to squeeze it in anyways. So we've got a question from Justina. Saying, I have a question about the data sets used to validate the CNN approach. In particular, you showed that there was a significant shift in the probability returned by the model. How comparable are the images used in both tests? That is, are these images capturing only a single state, since the probability vector returned by the model we proposed does not return the most likely state, but rather quantifies the amount of each state in given images? It is expected that it will have partial probabilities of multiple states for images capturing multiple, multiple states for images capturing multiple states.
Yeah, so I can probably not address this in all detail, but I think the general composition of the training sets or the two data sets was similar, with a similar distribution of features. But what changed, for example, were the noise characteristics, signal to noise, perhaps even the format requiring some interpolation, and these were the effects that presumably made the direct transfer somewhat difficult.
Okay, wonderful. Well, thank you very much, Hendrik. Really appreciate your great talk. So next up, we have, let's see, who we've got Giovanni Oakes. So. Giovanni, if you share your screen, it would be great.
Can you see my screen?
Yep, can see it great. All right, well, Giovanni, take it away.
Thanks. So, okay, so today I'm going to present a way of extracting virtual voltages for a 2x(n) array of quantum dots. And this work has been done with Jing Yu and John Morton at UCL, who have provided the experimental data, and then my supervisors, Alpha Lee, Charles Smith, and Fernando Gonzalez-Zalba. So in particular, I'll be looking at silicon quantum dots, where there are various proposals of how this can be used above the NISQ era, where we can take advantage of CMOS processing to have a very high qubit density. And because of no nuclear spins, we tend to have quite high coherence times with T2 stars of roughly tens of microseconds. But one of the problems with this system is that we have a lot of cross-coupling effects due to neighboring quantum dots. So if you vary one of the gates, it's likely to affect all of its neighbors, making it very hard to control each quantum dot independently. Currently, we're not in any sort of device in this sort of length scale or complexity, but instead we're looking at simpler devices such as a single silicon nanowire, where we effectively modify a typical CMOS transistor as least as possible by breaking the top gate into two and forming a quantum dot in each corner of this nanowire. And this can be classically modeled as a network of capacitors, from which we can derive a stability diagram, which has been mentioned earlier, where we can then figure out the occupancy of each quantum dot. And we have, for a double quantum dot, we have two negative gradients that are the transitions from the reservoir, which is from our source or drain, to one of our dots, or we have some positive gradients that are known as interdot charge transitions, in which we have an electron that tunnels between the two dots. So for here, we have an electron tunneling from quantum dot 1 to quantum dot 2. And if we extend the number of quantum dots, so for instance, for a 2x2 structure, we then have a much more complicated network of capacitors with many more cross couplings. And so as a result, we can end up having much more complicated stability diagrams, making it much harder to interpret what line corresponds to what transition and how to control each quantum dot independently. In this work, I'll be mostly considering reflectometry measurements, in which results in quite fast readout of our charge state, which allows us to make maps quite quickly. So one of the groups in Copenhagen has been looking at trying to characterize such a 2x2 structure by making one of their quantum dots a sensing dot and varying the other three. And they took slices in two-dimensional slices to then reconstruct this three-dimensional charge state, and then effectively moved in a combination of voltages to make this into sort of a triangle transition, and then showed that they could pulse around the 111 state. But this is not possible to scale up. Already it's hard to visualize 3 dimensions, and once you start going into hyperdimensional space, it becomes impossible. So there's a group in Van Sijpen's group and Pittar who have been looking at how to, in a 1D linear array of quantum dots, how you can use a combination of voltages to make these transition lines perpendicular to each other, so you can then be able to control each quantum dot independently. For a 1D array, we have fewer nearest neighbors, so this transformation matrix from this gate voltage to what we call virtual voltage space is quite sparse, as most of the values will be 0, and only we have values on the main diagonal. And what this virtual voltage does is effectively rotate our basis state by a certain angle, here psi 2, and then we also apply a skew. We're skewing the data and to make this other transition become perpendicular to it. And in our group, we've then extended this to find what this transformation matrix would be for a 2x2 array, and in more general for a 2x(n). And here we have multiple dot to reservoir gradients that we need to extract. And in order to be able to correctly label and specify which one is which, we envisage that we can take 2-dimensional projections of this hyperdimensional space by only varying 2 gate voltages at a time. And that would require us to take 5n-4 stability diagrams in order to extract the correct gradients. So we can then simulate what such a system would look like for a 2x2 quantum dot. So here we have a stability diagram when we're applying gate voltages simultaneously on all 4 quantum dots, and we get this quite complicated structure. And instead, if we then move to its virtual voltage state, a lot of these interdot charge transitions disappear, and our dot to reservoir transitions become perpendicular, making it much easier to interpret and also navigate in order to then arrive, for instance, into a state where we have a single electron in each quantum dot, which is what we'd probably want to be in order to initialize our quantum algorithm. So here we can see how this gate voltage, this matrix can be extended. So here we have an equation to extend it to a 2x(n) array. And here we have an image of what such an array might look like. Here we have a 2x8, which theoretically could act as a logical qubit. And then we can have this in a sort of grid-like structure where we could then implement our surface code and obtain quantum error correction. So we need a way of extracting these gradients, and we looked at common ways in image processing techniques, such as Hoff transforms or Hue transforms, where for each data point, we plot in polar coordinates every possible line that would pass through it. And then if we do that for every single data point, we then get areas in this Hue transform space, which bright spots, which correspond to our most likely gradients and y-intercepts. So we tried to use this transformation on some experimental data of a double quantum dot, and it turned out to be quite hard to interpret because the 3 intensity points that we observe here are actually the gradients that intersect this, both the dot to reservoir and this ICT gradient, so sort of the average that cuts across. And instead, the gradient that we are interested in ends up being this quite small hump over here in this theta histogram. So then we thought that maybe these histograms could act as a fingerprint, and that would tell us a specific configuration of capacitances. And so we created a large simulated data set, which we could label and train a regression model to predict the 2 gradients that we're interested from this histogram. And here we're only taking into considerations angles between 0 and pi/2, which correspond to only angles with a negative gradient. So we're already excluding any positive ICT gradients from the data. And then we looked at some experimental data where we had this 2x2 quantum dot, and we can see in the data set that we have an intruder where we have this transition that is probably like from one of the other dots that we're not probing, and also some noise occurring in the data set. And we can see that it gives us the correct average angles to result in virtual voltage space. I say average because on average, we are with angles perpendicular to each other, but because at such large voltage scales, the constant interaction model, so this classical model that we've been using, no longer holds. And we can see that at the extremities here, we have a slightly positive gradient, and lower down here, we have a negative gradient. And so we also looked at zooming in to a specific region where this classical model is more likely to hold, and also maintain some sort of noise in our data set. And the model seems to accurately predict the correct gradients. So then we did some statistical analysis where we subdivided the large data set, experimental data set I've shown you, into smaller and smaller equal sized regions, and then allowed the model to predict the angles that it thinks are present. And then, so here's the distribution of the angles. And then what we did was rotate our basis set into virtual voltages, and then manually measure the gradients and see how far off we are from 0 and 90 degrees. And our maximum mean squared errors tend to be reasonably small, so we're quite happy, although I think there's still room for improvement. And then the last step is how, so I've shown you how this is possible for a 2x2 by taking, for instance, multiple stability diagrams. But as you extend our nanowire, we no longer have, we will have some quantum dots that are not directly connected to a reservoir. So our idea is that we could potentially extend our reservoir by applying large voltages on the on the gates that we're not interested in, and then tune these or find the gradients for these 4 dots that we are populating at a time, and then the gradients that we extract are unlikely to be the exact gradients that we'll have, which we're then operating with, but could be used as a first approximation, and then fine-tuning could be done later as we start loading our nanowire itself. So to conclude, we have come up with an analytical solution for the transformation matrix for virtual voltage extraction for a 2x(n) array. We have also developed an algorithm to automatically extract the main dot reservoir gradients when only probing 2 quantum dots at a time. And we also think that this could potentially be used to map out how these virtual voltages vary in voltage space, which could also tell us how the quantum dot is behaving as we vary our gate voltages, and potentially could be used for tuning. Although there are already a lot of algorithms out there for automatic tuning, which you'll hear more about, I think, in the next talk. And here I would like to thank various collaborators and contributors. And for more information, there's a preprint in the archive, and also there's code available on a GitHub page. So thank you.
Wonderful. Thanks a lot for the talk, Giovanni. Questions?
I can't see questions.
So, Giovanni, I've got a question for you.
Okay.
So, I'm glad to see that I wasn't the only one who ran into problems using the Hue transform on this. I couldn't get it to give me anything meaningful either. Mm-hmm. But it felt like it was sort of like the way to extract this information. Yeah. But one challenge that I was running into with some of the experimental data that I've looked at is that there were problems with extracting the gradient because of the fact that the sizes of the cells would empirically end up looking a little bit different depending on where we were looking in a charge stability diagram. Mm-hmm. So my question is, how do you end up selecting a good region over voltage space to use this gradient identification?
Yeah, so at the moment, the algorithm isn't capable of determining which region you want. So it would be the end user. So that would be the tuning aspect, I suppose, of where you want to operate. But in the training data, we did use data sets that had like 1 or 2 honeycombs, or up to, I think, 5 honeycombs. So even quite large gradients or regions. But yeah, we did find that these are quite hard to interpret. Another thing we found that was interesting was that sometimes if you don't have reduce this down to a single line, like a single pixel, if you like, or if you haven't thinned your lines enough, you also get aliasing effects that make it harder to interpret. So yeah, it's not easy. But at the moment, yeah, we don't have a way of determining how large a window you want to measure, and we're leaving that to the user. If that answers your question.
All right, so we've got time for actually a couple of questions. So Hendrik had a question in the chat. So Hendrik, I think you're unmuted. You can go ahead.
Sure, yeah. So I was curious if you could comment how this method compares to the idea of just measuring how much any charge transition at one particular point shifts if you measure all the other, or if you change all the other gate voltages. So basically a more local cross capacitance measurements.
So you mean more what
Basically, you do a line sweep. You pick one point in your charge diagram on the transition, do a line sweep through that, so you see the transition between the states, and then just see how this transition shifts if you apply any other gate voltage. I mean, if you change any other gate voltage, and then you in principle get all lever arms in the system on an equal footing. It's of course a local measurement, which may be disadvantageous, but perhaps also simplifies things. So I'm curious if you have any insight.
At the moment, not really. I haven't looked much into the other just varying one at a time.
Okay.
I think, I think the issue there might be you might not know what charge state you're in. As you're,
that's true. You just get the response matrix.
But then the issue is you'll see a gradient which will give you it'll give you what it is in that local region, but then you might not know what your charge state is.
Yeah,
so it might be hard to determine.
The picture. Okay.
Oh, no.
The advantage could be that you automatically probe all dimensions, but maybe we should free up now.
Ideally, I think if you probed everything simultaneously, it would make it harder to interpret, but probably would be quicker. I'm not sure if that one, but at the moment, I don't have an answer to that.
Great. So we've got another question from Natalia. Natalia?
Yes. So I wanted to know. I cannot turn on my camera, can I? Oh, okay. Never mind. I just you mentioned that you can tune 2 by n, a 2 by n array, and you say, okay, I can open the dots so that I have omics and tune basically each of these pairs, and then you can fine tune. Do you have any idea of how big the effect would be, or have you made any estimation of what the effect would be in that array?
No, I don't know. I assume that if one dot is larger in this configuration, it's likely to also be once you've not opened extended the reservoir. So maybe the ratios are likely to be similar in both regimes, but there will be differences. But we haven't tested this experimentally, and it's something we'd have to do. At this point, it's just an idea of how this could be extended.
Yeah, I mean, in the end, you can do a quite quickly a kind of a capacitive model to see how much you would, I guess, you would shift it. Thank you very much. That was a very nice talk.
Thanks.
All right, wonderful. We've got time for one more quick question if somebody has one. Okay, well, if not, then let's thank Giovanni one more time.
Thanks.
And last but certainly not least before the break, we've got Dominic Lennon up.
Okay. Sorry, just having trouble getting my screen up. There we go. Okay, can you see my screen?
Yeah, looks great. Take it away.
Okay. Great. Okay, so after those great introductions to spin qubit tune-up and characterization, I'd like to talk a little bit more on really how to go about doing the coarse initial tune-up, so the very early stage procedures of even just getting to having any electrons trapped in the device at all. Very broadly, starting off with just the motivation behind even spin qubits, there are many other types of implementations, and of course the leading implementations are superconducting qubits and ion traps in quantum computation, but spin qubits present a very interesting and competitive solution to trying to implement a scalable quantum computer. And the idea in a spin qubit is simply to encode our qubit in the spin degree of freedom of an electron, or any spin particle with a spin. It does not have to be an electron. For example, it could be a hole instead. And this is quite desirable because they have a bunch of interesting properties. We have demonstrated universal gate sets in them. We can operate them at high temperatures. They are capable of being made in a way that is similar to conventional CMOS fabrication, as they resemble quite a lot conventional transistor type devices, and they can be very densely packed with a ridiculous density possible. However, they're still in their infancy at the moment due to a number of challenges, and one of these is just characterizing and tuning them, and this arises because of their variability. So the real problem that I want to tackle is that of confining electrons. And the concept here is that if we have some sort of uniform distribution of electrons or charge carriers at all sitting in a channel, and we have some gate electrodes patterned on their surface, then if we set a potential, if we set an electromotive force across the channel, then we end up with a current flowing, and we can measure this current. But if we set a gate, a gate voltage to one of these gates, we deplete the channel and we can't observe any current, so we have formed a tunnel barrier. We can do this again, and we can by applying to another gate voltage, and we can isolate a small puddle of electrons, where we can try now to isolate. We've effectively isolated these electrons, and we can try and interact with their spins, maybe form a single spin qubit. And once more, we can do this again, and we can form two isolated puddles, and they are very close to each other, so we can make sure they're tunnel coupled. So we can play with two single spin qubits, or we can form a single triplet qubit. This is about as far as I'm going to go with qubits in this talk, because a lot of it is even this is past the coarse tuning problem. Getting to just coarse tuning is easy in PowerPoint, but hard in practice. So to help give you an idea of what this of a physical system, I'd like to just talk about the device that I'm going to be considering throughout the rest of the talk. So this is a gallium arsenide heterostructure device. Instead of a channel, we have a 2D plane where electrons can move around, and you can think that the electromotive force is being applied at the bias. So we're observing this current here at I, and we can apply potentials to all of these gates. So it's got 8 gates just to form 2 dots. As we increase the magnitude of the gate voltages on these gates, we can see that the transport current through the device falls off, and we effectively see a transistor-like effect. If you think about where this transition from high current in the transistor to low current happens, it forms a kind of surface across the whole gate voltage space. So you have this is kind of like a surface where the pinch off is happening, or where we're forming tunnel barriers. And this area is very, very large, in sort of order of volts. But the features that we care about are very, very small, and they're order of 10 millivolts, say. So we've got a bit of a problem there. We've got a large, and it is 8-dimensional, I remind. So we've got quite a large problem here. Additionally, this type of measurement that we're doing here, where we vary 2 of the gate voltages to take a slice of the space, requires many, many little points to be measured. So we're doing a raster scan, effectively, a 2D raster scan of these points, and whilst observing the current. And this is slow, taking in transport 10 minutes or so, a good fraction of experimental time. So on top of this, no 2 devices are really the same. So no 2 devices are the same, or they're not even the same over a thermal cycle. So this also means that we can't copy and paste the gate voltage values across devices. So what can we do about this? The typical approach is just to do human tuning, where we take 2 pairs of scans. We do these windows where we do a raster scans, and then we make a decision above the raster scan, and we do another raster scan to make, using our physics knowledge, to iterate on this until we get to what we want. The automatic method that is probably the best to compare to is Bayesian et al., which is Hendrik mentioned earlier. And this is where we basically apply some set of rules, heuristic decision rules, to get to that will we make decisions off to get somewhere. This is nice because it can be made really fast, but it is not really robust to changes in the system or a new set of device architectures or tweaking. There are also a bunch of other solutions as well, but they all have slight problems. Like, for example, the optimizer solution requires is more local tuning, so you have to be close to where you need to be, and this requires some other coarse tuning solution to work the N+1 method. So we can think about this algorithm problem in terms of like generality to architectures and speed. Humans are roughly here. And the way we want to tackle it is we want to think about the slowest algorithm possible, but is very general, and then boost it up by suffering some generality to be above human tuning speeds. And what kind of algorithm lives in this space here? Random search, of course. So how we would apply this to this kind of sample is we fix a bias and keep it fixed at a small value. And then we generate gate voltage values that are completely entirely random from a uniform distribution, apply them to the device, and do our little red scan to check. We iterate this again and again and again. This is very slow, taking approximately 1 February to do from our approximations. When you're using February as a unit, you know that things are bad. So how can we speed this up? We exploit conditional dependence effectively. So observing event A gives us information about B. Clouds increase the probability of rain. And we can apply this in 2 aspects. We can apply this on how to sample decisions and make better decisions. And we can apply this to how to evaluate or investigate the device. So what conditional information is there to exploit? Well, on first, the tunnel barriers, we can we can get an information about where a tunnel barrier is forming by looking for this pinch off. Near this pinch off, we're forming a tunnel barrier, which is going to be blocking our current. And too far away from this, we can't see it anyway because our transport isn't sensitive. In a single dot, causes resonant tunneling effects, which cause peaks when you sweep a specific barrier in a specific gate in a specific way. And we can look for these peaks, and they give us information about whether there is at least a single dot present. And then finally, we can do these grid scans of measurements to try and distinguish what's going on. For example, if we see line patterns, we think it's a single dot. If we see curvy lines, then we can think it's a double dot. If we see nonsense, then, well, we try and determine what the nonsense is. So how do we apply this to the investigation of the device? Well, ignore how we make the decision for now. Imagine we are given a point and I'm told in gate voltage space, and you're told to evaluate it. The method that we employ is to progressively increase the to employ progressively more expensive measurements that provide information. So at first we would do a measurement, for example, in a direction U in some unit vector direction, a 1D scan, and check whether there is even a threshold, which would indicate that there is we're pinching off and we're forming a single tunnel barrier. If we don't, then we can move on to the next iteration and give up with that point. If we do, then we can do a small 1D scan and check for peaks. If not, then we can move on to iteration. If good, then we can move on. And then finally, we do a really coarse scan with some handcrafted features to try and determine whether it's any good for doing a full expensive measurement on, or just giving up and going on. Note these classifiers are just very simple. They're not machine learning. The machine learning really here in the decisions. They could be machine learning if you wanted to, and a lot of the literature could be slotted into these spots. But for now, these are just simple tests, really. And this is really beneficial to do this whole process because we rarely make it through the entire sequence. So we reduce the amount of time measurements that we have to make on average. Yeah, so how can we make, though, better decisions instead? Because that just reduced the characterization time, the amount of time it takes us to evaluate a point. So how can we make a better decision? Well, we can just take the data that is returned from the investigation directly and use that to inform our search. So we can redefine our entire search space instead of in a uniform volume and just going all over the place. We can just search near this surface. So we can redefine our search to be on a surface and search this surface uniformly instead. We can also exploit the information, additional information returned from other stages of the investigation to try and increase the probability of the investigation stage step returning true at various points. So what do we do? Well, first we use a Gaussian process, given some observations, to model the surface in 8 dimensions. This is 2D, but I'm using it as an illustrative example. This just models where we think the pinch off is going to happen for a given unit vector. We use this as a surrogate for the real device because evaluating on the real device would be far too expensive when we're doing these Monte Carlo type tricks that we're going to be using in a second. So what we want to do is we want to sample from this surface uniformly. We can't draw uniform random angles because that will oversample certain regions. So we use a Monte Carlo trick to try and get uniform points on the surface. We initialize a bunch of particles inside of the volume and we let them undergo Brownian motion. And whenever one crosses the surface, we log that point. And these points, given enough particles and enough time, are uniform on the convex shape. Yes, so that gives us uniform samples on this surface. And we basically have a list of points that are directions that are interesting. We then have another set of Gaussian process models that that model, for example, the probability of pinch given a direction and the probability of a peak given a pinch and given the probability of a peak given a pinch in a direction. And we multiply these together, and that effectively then becomes gives us a way of getting to the probability of a peak. But we have these separable models that are all being trained on different parts of the investigation steps. Finally, what we can do is we can just take our points that we'd sampled earlier, the uniform samples, and just weight them by the probability of a peak or whatever we're looking for. And then we can uniformly sample from this distribution here, which is effectively managing our exploitation trade-off, because we have a non-zero probability of sampling here, say, and that lets us start, as we are learning, focusing measurements on places that are interesting. How does it perform? Well, we have to evaluate. This is complex to evaluate because the devices, the measurements that come out are quite hard to interpret. So we get multiple domain experts to label them independently. And when we combine their labels with Bayesian statistics to try and get an estimate of the tuning time, we have two devices that we check this on initially, and in both cases we become under 3 hours, which is the threshold that we were told is human level kind of tuning. So we can consider this almost kind of superhuman, kind of, but not. It's a bit buzzwordy. What else? We test and do an ablation study to check the decisions that we make for the algorithm. Separate steps are worth including, and you can see that MUT, the expected time of tuning, falls on every case. And also we tested the idea of including extra gate architecture information, like grouping gates that perform similar roles. And this massively reduces times as well. So extra information can help. And we have since tried it on other samples and we've seen very similar results. So what more can we do with this algorithm? It'd be nice if we could tackle the device variability problem, which is the real source of all this problem in the first place, and hopefully one day make this equal instead. So imagine we have two devices. Again, these are illustrative, really. They are normally much more complex than this and not linear. But what we effectively have is a uniform sampling tool, so we can do something with it. What we can do is we can try and uniformly sample point clouds from both of the devices, and then try and learn the transformation between them. This is effectively point set registration, which is quite a common method in computer vision literature. So what we do is we do something very similar, and we apply this method here, coherent point drift, and restrict our transformation to be a linear transformation, but without translation, because that has a physical interpretation in these devices. And when we did this in practice, we did it on the devices I was talking about earlier. So we try on a device over a thermal cycle, and you can see that the linear transformation matrix is effectively just dominated by a change in the scaling factor. So this basically means that our volume has just shrunk by one uniform scaling factor. And when we did it across devices, we end up with a mess and all kinds of different changes required. Probably they might even be non-linear. So it's definitely a big difference between these samples, but a bigger one than between over thermal cycle. The code is available on GitHub, called Autodot, on our group GitHub, and it's agnostic to experimental software. So if you've got Q codes or anything like that, you can try employing it in your devices. It's still a work in progress, but it's in a usable state, and the investigation steps are configurable, so you don't have to stick to the ones that we did. Thank you for listening. And thank you to all these people who made this work possible and were part of the work.
Okay, well, wonderful. Thank you very much for a great talk. So any questions? Oops. All right. So I guess if there's no questions, let's thank all of our speakers one more time. And now we've got a break. The break is stretching from right now to the to 2 o'clock GMT. So yeah, thank you very much, everybody, for attending, and yeah, hopefully I'll see some of you in the coffee break.